am Milan from Keytech, and in this video we will briefly go into our control cabinet and show our software step by step how we build our own PLC. We will also show this live here on our machines. This here is our lab line. We always have one standing in the hall, and here you can see our current status with the software. We have our own HMI panel, which then controls all the machines running together here over LAN cables. You see a visualization like never seen before in the industry. Everything is perfect, responsive, almost live. Connected here with the Winder. This is basically the current state. However, this is not our first software. For about 5 years, we have been developing our own software for machine control. Everything started back then with our first mini winding machines. I programmed them myself back then with my modest programming skills using these ESP Drinos, which are basically ESP in Arduino format, and then a CNC shield. Back then, the thing was, all my startup founder friends had released an app and I wanted an app too. So I basically started with ESP Drino and Blink, a kind of thing where you can build apps to connect that together. That means the Winder then communicated with our laser measurement via an American cloud server, and you could control everything by phone, by app, and I thought that was really cool. But then we showed it to the first customers and thought it was cool. But the customer really didn't find it cool at all. He found it terrible because he wasn't even allowed to just log the device into his Wi-Fi. So for the solution, you basically needed the machine constantly in the Wi-Fi, and as soon as the Wi-Fi was interrupted, the machine shut down. So that was not such a smart idea and nobody wanted it. The customers wanted fixed wiring solutions again, but at that time we also didn't see the point, or we simply didn't have the money to buy such expensive industrial electronics. That's why we then thought we'll just build our own circuit boards and had our own boards manufactured with JCPCB, and those were basically our Winder boards with the stepper motor drivers, etc. And they were then sitting in the back of the Winder. The Winder, our winding machine, didn't have a control cabinet before, and we just had this board. That was really cool because the board cost 100 euros and you can connect everything easily. But due to the USB connection, the whole thing was extremely susceptible to electromagnetic interference, and it was extremely difficult to build solid software based on these USB things because there were frequent connection interruptions. Additionally, you always had to set up a laptop and install a lot of drivers so that these USB things could all communicate with each other. Overall, the whole system was quite fiddly and annoying, and many customers didn't want the dependency on some strange circuit boards that only we order from China. And many customers wished that we would finally install proper industrial electronics. After our own circuit boards, we briefly tried industrial Arduinos, because we come from the Arduino world. Then we thought, let's take an industrial Arduino that can also be mounted on DIN rails. But the system was also just way too fiddly to build a proper industrial plant with it. We are moving more and more from the research area into the industrial area, and such a system doesn't work there. And if a single component was broken, you had to throw the whole thing away and rewire everything. And that just doesn't work if you really want to build a solid machine in the long term. So we discarded that relatively quickly. And that's when the idea for this control system came up. And in this generation, we basically decided, okay, it really makes sense to install certified electronics from Siemens, WAGO or BECKHOFF in the control cabinets. Not only because they are certified, but also because they always provide delivery guarantees. That means basically I can be sure that I will get these terminals for the next 20 years. This means the control cabinet can be repaired again and again for the next 20 years, and that's really valuable. But what we didn't want is a Windows 98 touchscreen interface or these licensing fee models from Siemens with the TIA portal or from BECKHOFF with TwinCAT. And we also didn't want to program in some old awkward programming language, but rather in something modern like C++ or Rust. And so the idea for this new control system came about. And this is basically what resulted. And here we have our own system, and Philipp, our head of software, will elaborate much more on it shortly. But this is essentially the system we have now established. The entire software is in Rust, front-end with TailWind. It then communicates over LAN, over EtherCrab, with the individual control cabinets, with the individual machines. All the machines can communicate with each other in real time. We have distributed clocks, and we have installed the real-time kernel, and this way we can have a perfect solid machine control even though we don't have a crappy interface. The idea of this control system is basically to use the certified electronics from the big companies with delivery availability in the control cabinets, but to combine that with modern high-level language, with Rust and custom software that can be freely written. And over the last few weeks, we have posted many videos, and there was also a lot of hate, and there were also many different comments saying that it's an isolated solution, that it's extremely bad, that you can find much better people who can just automate a Siemens thing. And the thing is, you always have to consider the context in which you see it. And for us, the context is that all our employees come from their university, so they are learning or they all want to do Rust. They don't want to learn some weird old TIA portal programming language. And that means we also have specific requirements with these small machines. This isn't a nuclear power plant, so for us, safety doesn't play such a big role. We've solved safety more on the hardware level, with emergency stop, with burst disk, with automatic shutdown. If I were to build a nuclear power plant now, I would of course have also relied on a Siemens control system, and the videos sometimes have sensational titles or thumbnails. That doesn't mean we deny Siemens any right to exist. It just means that in our context, this control system makes a lot of sense, and I think the control system also makes a lot of sense in the context of other companies that build similar plants with many stepper motors, with many individual machines that all communicate with each other. Exactly. Now from the outside, our filament line might look like a trivial system. Plastic goes in at the front, gets melted, and we wind 3 printing filaments onto some spools. The whole thing is actually not trivial at all, because for example, in order to process recycled material, all machines must communicate with each other. That means the laser measurement notices, for example, hey, the filament is too thick, too thin, then adjust the speeds here and just the speeds alone. So basically how this roll moves here, depending on how the arm is, that determines the load or the tension on the filament. In doing so, this must always turn precisely, and for example, just this load arm, it's a geometric simulation to always have the perfect speed here, because you can't just set a speed, but you always have to set a specific speed as the circumference of the spool increases over time, since more and more filament is wound. In other words, you have to simulate it relatively complicatedly. And precisely all these things we can simply write in Rust instead of somehow. So try solving this with a ladder diagram or somehow in Siemens Portal. It's just much cooler that we can work in Rust, simulate the whole thing. And I think that is the future. The important thing is our software is also completely open source, which means every customer can theoretically tinker with it. And here you can see it is being synchronized live from GitHub all the time. If you want to log the machine into the Wi-Fi, then you can see all the different versions live on GitHub and can always download new versions or build your own versions. And how the whole thing works, how our software and the entire architecture from BECKHOFF over Ethernet, EtherCrab, and then the HMI displays, how it is all set up, that will now be explained by our head of software, Philipp. Yes, there was one more thing I had before. Very important, as multi people have also written, why do you make such complicated software for your machines? You might build 10 per year. Just slap Siemens on it and it's done. The thing is, there's another reason for this. We've had a little secret project running here over the entire last period. This is the bottle cap sorting machine. It's a machine that recognizes bottle caps by color using image recognition and then sorts them individually into different containers. And this way we get clean, recycled granulate. This is a small research project of ours, and for that we need AI and automation. So we need reliable industrial electronics, real-time speeds, but also the latest AI models, and how that works with our new Rust software, because that way you can freely program something like our image recognition model and integrate the latest things available in the software world. But at the same time, we still have our industrial electronics and can control all the pneumatic ejectors here. And that's basically why we said, hey, we want to build something modern based on a high-level language or low-level language, which Rust actually is, and not Siemens TIA Portal. Because try building a bottle cap detection based on AI in Siemens TIA Portal, at the latest, that's where everyone hits a wall. At that point, all these modular systems like TwinCAD, TIA Portal, codes reach their limits. And that was essentially a decisive factor for why we said, hey, we want to build something of our own. That's basically the context for why we made this decision. More on that later at the end of the video.
Okay, so first I will explain how everything works with the control cabinet, and then we will go up the levels until we have shown how the touch panel works. Exactly. And that's why we start right at the bottom on the hardware level, and some of you might not know this, but what is this this BECKHOFF system that we keep talking about? And ultimately, BECKHOFF is a manufacturer of a so-called field bus system. And a field bus system is basically there so that we can connect a PLC, that is a computer or a laptop, with electronics. That means over a network. It is important that we have devices, sensors, and motors at various points. When building a large machine, you also have greater distances to cover or sensors that are a few meters apart. For that, you need a professional field bus system. And ultimately, we chose BECKHOFF because they have a very solid field bus system. And they have a large selection of components. And ultimately, the first component you need is a so-called bus coupler. It has 2 Ethernet ports here and a few connections for power. And then here on the lower side, there are these pins where you can, in a kind of slot mechanism with a sliding mechanism, connect more terminals. And then they are all connected to each other through these pins. Exactly. Here, as an example, a LAN cable. It simply goes into the first port. And here I can now connect my PLC or my computer on which the software runs. And in the second LAN port, I can plug in another LAN cable, which then runs to the next bus coupler. This way, you can virtually distribute the machine locally.
Yes, that's basically how we do it between our machines here. That means from the HMI display, it goes to the extruder. From the extruder, it goes a bit to the winder. And that's how we've basically set up our network and for laser measurement.
Exactly. And now we can take a look inside the box here. There are a lot of red boxes, but they are all different. Ultimately, you need to know there are different types of terminals. So there are ones for analog input, ones for analog output. That means they can measure and output voltage, but there are also digital inputs and digital outputs.
Perhaps now, practically speaking, here at the extruder, we have 3 heating zones and 3 temperature sensors. And for the 3 temperature sensors, we need 3 temperature sensor terminals, PT100 terminals. And for the 3 heating zones, we simply use digital outputs to control these SSR relays so that they then send power to the heating elements.
Exactly. For the temperature sensors, for example, we use these EL3204. EL is simply the class of terminals we use, 3000, you can already tell. And this is an analog sensor, but we also have other numbers here like 2004. 2000 are digital outputs, and in this case it means that it has 4 channels, so 4 digital outputs. The 4 digital outputs can be used, for example, to control these 4 SSR relays, which allow us to tell the machine, hey, heat now or don't heat now.
The good thing is, because everything is built so modularly and you can slide the clamps in and out individually, you can, for example, if this clamp is defective, which controls the motor, simply slide it out, insert a new one, and then just continue.
Exactly. And here is one that's very important for New Window, 7041. It is used to control a stepper motor. That means we don't have external stepper drivers. They are directly included here.
We mean stepper motors, before the whole thing comes up in the comments again, that we in English.
Anglicisms. Okay. Exactly. They are all basically in here, nicely wired, and these LAN cables are basically connected to the outside here. That means, it already says here, the monitor goes to this port and the window goes to this port.
This is basically the input and output.
Yes, exactly. So now let's take a look at how the machine is generally wired ultimately. It starts here at the HMI panel. Here is a LAN port, and this is our LAN cable. It goes here first into the extruder, into the bus coupler, and from here there is the second LAN cable over here to the bus coupler of the window.
Is that already tied in there?
Exactly. And this is now the last machine, which is why there is no output LAN cable here. Now let's take a closer look at the HMI panel. Ultimately, it is assembled from a mini PC based on an Intel chip and a touch display. That's basically the hardware.
It must be said that you could also simply install our software on a regular Linux PC and then control it with a mouse. But we wanted everything to be connected in such a panel. That's why we soldered the mini PC with such a touchscreen here. Both standard components from Amazon, to be honest. And so we have it nicely and touch-friendly, but it could also run on any Linux computer. If, for example, it were to break and we no longer have spare parts in 20 years, you could simply load it onto a normal PC because there were somehow 1,000 comments about it.
And maybe why did we actually choose Linux? Well, our opinion is that Windows is generally outdated for industry. And Linux is actually quite modern, and we could have also chosen macOS, but then the machine costs would have been a bit higher, and ultimately on this panel a special Linux runs, and that is NixOS. And the real nerds among you will already know what it's about. Ultimately, NixOS consists, or the great thing about NixOS is that we can describe our entire operating system, everything that is installed, what is configured in a few files. That means no one has to sit down and manually install all 10 programs we need here. Instead, we insert a stick into a new device, install the basic version of NixOS, and then run an installation script that loads all our software, configures everything, even the desktop wallpaper and the user's name. Everything is controlled via an installation script. And that's really nice because it means we spend very little time setting up a new device, and it always guarantees that every device is the same.
Yes, because that used to be a big problem when we still had these here. We had circuit boards, you always needed thousands of drivers, and every customer somehow had a different laptop, and then it was always like, yeah, which drivers are installed? And so we have virtually eliminated all this uncertainty that comes from the operating system, because now whenever we send updates, we basically wipe the operating system and install a new one, and then it is always perfectly the same.
Exactly. Ultimately, it is rather common in the industry that a machine, a single one, is programmed once, then shipped to the customer, and then it never actually receives an update again. But we are a modern company, and just like Tesla updates its cars, we want to be able to update our machines as well. That is the only function for which you need Wi-Fi on this machine. That means if we did something wrong, or if we want to offer the customer new features afterwards, then we can apply an update to the system. What's quite interesting here is that it's not like in the App Store where you just click on update, but we update our entire operating system. That sounds a bit weird at first, but it has a few advantages. The update system is managed through NixOS. This means if something goes wrong, the old versions are still installed on this computer, and we can simply revert to a previous version. And this is possible not only in the interface, but also in the computer's boot menu. This means there is absolutely no way to brick our system because we broke something in the software.
You have to show how nice it is with the updating.
Exactly. And what's also interesting about updating is we don't have an update server with various ready-made applications, but we can directly select different branches from our GitHub. And it ultimately works like this. When we select a version here, it is cloned onto this computer with git clone, and then an installation script is simply executed. This means that when we create a new version, we can also adjust the installation. Exactly, here you can click on branches and then select individual development branches. If they are grayed out, you can see they are older. If they are not grayed out, you can see, this might be a newer version. This is always quite nice for us because we really have a lot of branches. And then it installs itself, and oh yes, here you can see all the old versions in the installed version. That means at some point we had a test branch here. I can just click on select, then it takes a moment and the system boots into the old software, and that really happens within seconds.
Ta-da!
You can count now. Exactly, here you see the boot menu where you can select the old versions.
Now you've probably loaded some weird branch, yes, because nothing will work anymore.
Certainly, certainly. All branches work for us, always. Okay, what next?
How is the software written? Is it Rust, TailWind, Electron, Socket.io? You still need to explain that.
Yes, there's something else before that. Exactly. And what's also quite interesting about the update system is that we really only have our GitHub repository and no precompiled binaries. That means when you install a new version here, the Git repository is downloaded and the software is compiled on this device. It actually takes 10 minutes for such an update to be completed, but it has the advantage for us that we don't have any infrastructure, no infrastructure that needs to be maintained, just our GitHub repository. And we always say, hey, we are open source. Ultimately, there are two sides. On one hand, the software we use is open source, and on the other hand, our software is open source. We had already considered whether we could make this system available to other machine manufacturers, and we have already talked to people, and they gave us feedback that they don't want it to be open source. And with this update system, it is also completely possible to use private repositories and thus not be open source yourself, but still use open source software. Exactly. And ultimately, two things run on this panel. So our control software is not just one software, but basically two. And we have this interface that you see here. This is our Electron frontend, we call it that. It's just an app that you can close and reopen if you want. And the second part is essentially our backend, which is programmed in Rust. So the two software parts also have completely different programming languages. In the front end, it's simply TypeScript, and it's an Electron app. Electron app means it's like a Chrome browser that only loads this one website and doesn't have a search bar at the top. And we can build our interface as if it were a normal website. And the advantage is that anyone familiar with web technologies can contribute to our software. And most students have already built a website before. That means they can navigate the system very, very well. In the browser, our website runs, and our website is built on React. So React is a JavaScript front-end technology. It's pretty much the most well-known, largest, and most popular. And for this reason, we chose this, and the components we built here are styled with TailWind CSS. So for all of you who do web development, you know what it's about. That's just another way to describe styling of a website, and we've often been asked, hey, that looks pretty cool. How can one have a UI like yours? These are basic components that we used called share CN. That means we simply copied them and then adapted them for ourselves. In general, the UI concept is very modular. This means that if you look closely, we actually have only a few components. We have this component, for example, where a number is displayed with a graph. You can see it here, 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 here. Then we have the component that allows you to change a value, and this component is really the same everywhere. And that means we coded it really well, really nicely, so that you can change the values in all possible ways. I can press plus here, press minus, I can move the slider, I can open a numpad here, and then enter my number. And down here, I'll say, there are always the buttons to cancel, save, or return to default if you no longer know what the default was. Then we have a few more buttons, for example, for the laser pointer or to start the homing routine. And these are the same buttons used here in the mode where we can switch between operating modes.
The whole thing is always modular. As you can see here, you have the same tiles and always these small graphs in the tiles.
Exactly, and that leads to us being able to develop the UI very, very quickly, and there's really no discussion about how it should look because it's a very limited system that looks good. And then we have a few special places where we said, hey, that makes sense. We programmed special visualizations. That means, for example, we now have the visualization of the load arm. This is simply a graphic that moves according to the angle. The second visualization we built here is this bar where you can see the current position of the traverse and exactly where the limits are. And the third on the side is this virtual spool which moves at exactly the same speed as it does in real life.
That would be hard to get in one frame at the same time, but trust is hard.
Exactly. And each machine also has almost the same layout of the tabs that are up here. That means first there is the control page. That's where the operator will spend most of the time. Then there is the graph page. The graphs are all the same. They are just colored differently. And here you can always see the values, different measurement values or different speed values.
The values here are relatively unspectacular, but it gets exciting when we activate our laser measurement, because then we get live values of how thick the filament is. This is extremely important because it's all about producing perfect filament with perfectly consistent thickness. And then you can see, okay, here, this is my extruder speed, this is my diameter tolerance. And what we also built, you can see down here, is an export of all the values. That means the user can, at the end of the day, when they have completed their experiment, export everything and then have an overall analysis of everything. And if they want, they can print out the diameter of the filament spool, export it, and then stick it on as a label so that when the spool is sold, one can see, it has exactly this perfect diameter.
Exactly. Then thirdly, there is the config page. It contains some more niche settings, such as which algorithm is used for the speed control of the coil.
Or now here also brand new machine connection, how to make the connection between the machines.
Exactly. Then there is the manual, which is ultimately a long interactive document containing all the safety notes and screenshots. That means you can learn how to use our software through it. And then the last tab is called presets. It works in such a way that you can save the settings you made on the control and config page. That means for this blue coil, you have to set the flank sides, how far they are in millimeters. And when you switch to our metal coil, it is a bit wider. This means you can save a preset where the values are pre-configured, which ultimately makes the process, for example, of changing spools easier, or regarding the extruder, we can save the values that worked particularly well for a specific plastic.
For example, we have transparent, where did we just have it? Transparent PETG easy. That's basically for this transparent PETG that we produced yesterday, where the guys, of course, didn't clean up.
Exactly, and you can also export that as a file, and that means if you don't just want to buy one line but 10, that means you can test on one line and then transfer the settings via USB stick to the other machines, and then the entire production process is really the same, and you don't need a notebook, as is often the case in research facilities where you have written your daily notes somewhere. Okay, so when the software is started for the first time, it checks, the backend checks which machines or which devices are actually connected. That means we now support two types of peripherals. One is USB for the laser, and then it's EtherCAT for our main machines. And ultimately, the EtherCAT network doesn't even know where one machine starts and the other ends. Yeah? And that's why we get a whole list of devices in our network from our open source library, EtherCrab, that we use. And here, for example, you can see EK1100, the bus coupler. Down here is another bus coupler. And now the question is, which of these devices belong to which machine?
Each device is essentially a kind of clamp. Exactly. So a bus coupler, a temperature sensor.
And the problem could also be that we have installed a terminal twice in different devices, or that someone building the control cabinet puts them in a different order, because normally the function of an EtherCAT device is determined by its position in the network. And that's why it's also normal in the industry for software to be written for a specific machine, but we had the special requirement that we wanted to write software that is compatible with different machines, essentially a large monolith. And that's why we had to find a way to determine which device belongs to which machine. We came up with a little hack, because the problem is that all these devices have no serial numbers. So the serial number is always 0. That means if you have a 2200 terminal and another one installed, you really can't tell which is which. And the cool thing is that all these BECKHOFF terminals have a small chip called EEPROM. And on the chip, there is some information stored, like, for example, what type of terminal it is. And we found a way to store a few bytes in this EEPROM. And these few bytes then tell us, hey, what is this device actually for? And you can see that here it is also displayed in the table. That means we have these 3 columns: the designated machine, the serial number, and the device role. That means, and there is a 4th one, which is the manufacturer, but it is hidden because the manufacturer, which is always us, is Makatech. That means this bus coupler says, hey, I'm from the extruder version 2 and I have the serial number 4. That means we know all devices that also belong to the extruder version 2 and have the serial number 4 are theoretically one machine. So, and then we take these devices and then we pack them. Then we basically check with a checklist, are all device rows there? That means, do we have the bus coupler? Do we have this digital input? Do we have the interface for the inverter? And if any of these devices are missing, or any device is duplicated, or something is there that shouldn't be there,
So for example, there would now be a temperature sensor clamp, a fifth temperature sensor clamp, even though we only have 4 temperature sensors.
Exactly. Then there would be an error and the machine would not be recognized. But if everything works, then these devices are stored as belonging to a machine. That's why we have this other machine tab where you can really see, yes, here we have the extruder with serial number 4 and there are no errors. So that means this green check mark. If a terminal were missing in the control cabinet, it would say here, hey, I'm missing the device with role 2 or something like that. Yeah,
The cool thing is at the beginning, you have to say, hey, this temperature sensor terminally belongs to the machine and does the temperature thing and ISO.
Should I show you how it works?
And that even works with such a touch display.
Exactly. Ultimately, when we set up a machine for the first time, these values are not saved. We can connect them here, we can start the panel, and then there is this edit assignment, this dialog. And there we can simply select which machine it belongs to and enter the serial number here and choose the role. And that's also smart because for the EK1100, it can only be a bus coupler. That's why you can't select any other device role. So it's basically for dummies, so you can't do anything wrong. And then you write it once into the EPROM, then you turn off the machine, restart it, and then the values appear here, and we can properly recognize the machine. And these machines that are displayed here are exactly the ones for which there is a tab on the left side. The Winder is an EtherCAD machine, the extruder is an EtherCAD machine, and then we also support serial. That means this is the USB to ModBUS converter, and you can see it. You can simply pull it out and plug it back in, and it will always be recognized anew. Exactly. That's how it looks. Then I can tell you a bit more about the code. Okay, and maybe I can say again, why did we actually choose Rust? Ultimately, we had turned the camera on me again. And another question we can answer, why did we actually choose Rust? Actually, we had the choice between 3 or 4 different programming languages, C, C++, which are both classics, Python and Rust, because we looked at what libraries are available, open source, that we can use to control our EtherCAD, our BECKHOFF devices, and for that we need a library, which is then an EtherCAD master that initializes the network and so on. As there is an EtherCAD master called M, I don't even know what the abbreviation stands for, in any case I believe it is programmed in C, and there is also a wrapper for Python. But Python is completely out of the question because it is not a real-time programming language. It has a garbage collector, is generally quite slow, so it was not an option for us. And then of course we had the choice, hey, do we take an old programming language like C, C++, which of course has very valid use cases, or do we choose a more modern language like Rust? And then we decided on Rust for several reasons, because Rust has a set of rules that contribute to making your programs memory safe. For us, this ultimately means that when we write the code and it compiles, we have very high confidence in the code. That means when I write code, I know 90% of the time it works now. There might be logic errors, but the program doesn't just crash randomly. And I would say I wouldn't feel as confident with C++ code because there are really a lot of foot guns, a lot of pitfalls you can stumble over where you might get a memory fault and then end up debugging for hours. And ultimately, with Rust, yes, it's harder, but the time you need to overcome these obstacles, as some say, that Rust puts more in your way, you solve them here at the computer. And then you don't have the problem that issues arise when the machine is already programmed, because that's a pain, as then it's at the customer's place and you have to go there. That means you'd rather have the pain in the office, but later it's more relaxed and you know the software works. And it's also a very modern programming language. So there's a great package manager, very ergonomic, as they say, very idiomatic. So it's extremely fun to write once you've gotten over the hurdle of learning it. And also an interesting fact, Rust is the language according to the Stack Overflow developer survey, where people who most according to the Stack Overflow developer survey, it is the programming language that developers most enjoy coding in. So it's not the most popular programming language, but when it is used, people are very, very happy with it, with 86% right before TypeScript, which we also use. That means you can definitely guarantee that if people work with us, they will have fun, just because of the programming language.
yes, maybe you also have to consider it in context, because many have written, yes, you will never find anyone for these strange niche languages. So the thing is, we are here at TU Darmstadt. Our hall is 5 minutes from the technical university. That means for us, Rust is the way to go, because we find many people who are interested in it. And if we were to tell them now to program in FUP or whatever for some Siemens TIA portal thing, they would run away screaming.
Yes, and ultimately, yes, Rust is a relatively young language. It has only become popular in the last 10 years, and maybe in 2015 it wasn't very stable and not very usable, but now in 2025 Rust is very usable. Miss Maassens. And actually for me it's a no-brainer that other mechanical engineering companies or hardware companies also use Rust, because they have exactly the same problem as we do. Once the device is shipped, you can't make an update anymore, and you want things to just run smoothly. Whether it's a nuclear power plant or a satellite, the software simply has to work. And Rust helps you build stable software. And that's why it might still be a niche for you now, but we think that Rust is definitely the future in mechanical engineering. Okay, then I can tell you a bit about the code. This here is GitHub, so it's basically Google Drive for developers, and that's where we store all our code. And it is public, which means you can simply go to GitHub, to our profile, to our repository control, and then you can also look at the code if you are interested. And ultimately, there are a few folders here where the different things are. For example, we have the folder server, which contains our backend, so that's where the Rust code is. Then we have NixOS, where our HMI panel is configured. Then we have EtherCAD HAL, which is essentially an abstraction layer for our EtherCAD devices. This means it contains information about which bits and bytes an EtherCAD device sends and which it requires. And EtherCAD HAL derive is basically a parallel crate to it, where there are a few macros. So for those who have programmed in Rust before, this might be interesting. Then Electron is our front end, meaning all the front-end code is in here. We also need docs, of course, a bit of markdown documentation, and control core is another Rust crate that abstracts away some of the server logic so that it can be reused, and theoretically other applications can be built on it. Right, what you can see here is that we can create the releases. That means in our Git tree, we can simply create a tag, for example, the tag 2.5.0, and that is the tag that also appears on the machine where the customer can pull an update from. Yes, exactly. What else do we have? What else can we explain? Right, so we also use GitHub issues. That's basically the project management for developers. And everything is in there, all the tasks that need to be completed, all the bugs that we somehow notice. And then we can say, hey, Robin is doing this now, Philipp is doing that, and so on. And if someone has a solution for an issue, then there's a pull request. And in the pull request, you can see, hey, for this issue, there is now a description of what was changed. And then you see on the left side how it was before. And for example, this comma was removed, and then this comment was written there. And in this way, there is also a kind of quality control among the developers, so they can really see, hey, what was actually removed and what was added. Does that make sense? That's the development process. Exactly. Here we also have an architecture diagram in our documentation. That means first the hardware level is described here, consisting of the bus coupler, all the terminals, with which we can then communicate via EtherCAD. And we do that via EtherCrab. That means that is the layer that comes directly above. And then we have our EtherCAD shell, where the entire abstraction of the individual terminals is included. On top of that comes our logic, like for example from the window. The logic is then split again into the logic of the tension arm, the puller, the traverse, the laser pointer, and so on. It is all split up. And this window then has an interface to the front end. And our interface works in such a way that we have a RESTful API and we have a WebSocket API. The RESTful API is there to change something on the machine. A change is basically when it is said that this value should be changed, this button was pressed. That means everything that goes from the front end to the back end goes through REST, and everything in the other direction, from the back end to the front end, we do via WebSockets. With WebSockets, the advantage is that we have a very lightweight, very fast updates, and that's why we can also display these live graphs, because all values are pulled via WebSockets.
Clear the seats because it's so loud.
Okay, and for the WebSocket events, we also have two caching layers. So we have a caching layer in the backend and in the front end. This means that even if you close and reopen the front end, all values from the last hour can be reloaded from the backend. And in the front end, we naturally need a cache so that we can display not only the latest value, but the entire series of values. In the front end itself, there is actually no machine logic. This means the front end is entirely there so that the values can be read and written from the API and displayed in the UI. That means we have basically a big React hook called useWinder2, and it contains all functions like rotate at speed, turn the laser pointer on and off, and through it, all values can also be read. And then we have our generalist components, which I just explained, to change a value, to press a button, and so on. And from these components with the hook, the different pages are then assembled. That's the software architecture from the very bottom to the very top. Another reason why we configured our own Linux system is that it is very important for such an industrial process that we have real-time capabilities. Real-time means that we always perform our actions at a specific point in time. This means it cannot happen that if the computer, for whatever reason, is theoretically slow, our machine doesn't get an update for 1 second, because then maybe the filament goes bad, someone gets hurt, or whatever. This means such industrial systems must always be real-time. If you have a normal microcontroller, then they are actually always real-time, because they only have one card, they don't have an operating system on them, and they just work. But we have Linux here, and Linux has other things to do. It still has to render the image. It has many other tasks to perform, and that's why we need to configure our Linux so that it gives our process a real-time priority, so it is always executed or with a very, very high priority. And this has to be done on different levels. The lowest level is, of course, Linux. It has to be configured to support real-time. That's why we have the Linux kernel 6.12 on it. It's not that old yet, because this real-time system was developed over the last 20 years, and now at the beginning of the year, it was basically completed after 20 years. So basically the perfect time for us to use this system in production. Then it is basically activated on the operating system, and then we can use a special line of code to specify that a certain thread of our program should now use real time, and we tell the thread that handles communication with the machines, hey, you now have real-time priority, and that's why you can be executed particularly quickly. And then there are, of course, a few other things to consider, like ensuring that the resources within the program do not block each other, so that the program can really run quickly. Exactly. Okay, what is this EtherCrab library that we always use? EtherCrab is basically there so that we can interact with our EtherCAT network using Rust. That means EtherCrab scans all devices, tells us which devices are there, and then sends the data to the devices for us and retrieves it again. With EtherCAT in general, there is always a packet that goes through the entire network and then comes back. And this packet is built, sent, received, and so on by EtherCrab, and we just have to send the individual data to the individual EtherCAT terminals, exactly. And now the question is, what kind of data are we actually sending and receiving? And we didn't really know that ourselves at the beginning, because it's not, it's public information, but it's buried deep in the data sheets and not really readable. And that's why we got an official version of the BECKHOFF software, connected it there, and then checked in the interface what kind of values are actually being sent. Are they bits? Are they bytes? are they some integer values or float values, and then we basically replicated that one-to-one. Normally, this is found at BECKHOFF in so-called ESI files, and instead of these ESI files, which we do not use, we programmed our EtherCAD High, where there are encoders and decoders for each device. And here in our repository, there is now a guide on how to view in the TwinCAD software what it looks like, then a diagram of the inputs and outputs, and how you would then implement that in code. That means here you have, for example, a Rust struct called AI standard. This is not artificial intelligence, but stands for analog input. And it is basically there to measure a volt value or a current value. And the important thing is actually the value, which is an unsigned 16, meaning we have up to 16-bit analog input, whereas the terminals actually have something more like 12 bits. This means the resolution of the protocol is a bit higher than that of the actual terminals, and then there are a few more values alongside. Here, for example, we have an overvoltage or an undervoltage. What you can also do is configure limits in the terminals. Then it says here somehow 5 volts were exceeded or not reached, but we don't use any of these features at all. We only use this simple value. There is also another PDO object called AI compact, which also only contains this analog value. Because this is an analog input, meaning it's a value that only needs to be read. And that's why we have this read function here. This read function essentially receives a bit slice. A bit slice is basically just a series of individual bits and then reads these bits and puts them into the variables. That means under voltage is the first bit, over voltage is the second bit, and the last 16 bits are basically our analog value in the, I think, least endian or lower endian it is. This is basically the order in which the bits are. Exactly. And here we now have a guide for various terminals, some of which also have outputs or have outputs and inputs at the same time. And then the code looks a bit more complex, and some have told us, hey, you probably don't test any of this at all. No, especially this part is very well tested, and we also use unit tests everywhere else in our software.
Exactly. What else do we have?
Here is, for example, also a guide included if you want to implement a driver for such an EtherCAD terminal, what you need to consider. And that's really a long list of what you have to do here. But you do it once, and then you can use this terminal forever in all devices. In our backend software, after we have identified which devices and which machines are present, there is the control loop. You probably know this if you have ever programmed Arduino. There is simply this loop function, and we ultimately have this loop as well. It is a thread, and it works in such a way that we first send the EtherCAD packet through the network, wait for it to return. Then we read all inputs from all input terminals. Then we execute the machines. That means the machines can then calculate their logic. They read the sensor values, then write, for example, a new speed for the spool or whatever logic they have implemented. Then they write the outputs, and then the loop starts again. Then the new packet is sent, inputs are read, machines are executed, outputs are written, and it continues like this in the loop. And this loop thread is also real time. So I can show a few examples of how we implement such a machine. And in the server folder, there is simply a folder for each machine, for example, Window 2. And since we just talked about the loop, here is, for example, the loop implemented for the window. That means the main loop calls a method in each machine. And here it says, here are a few high-level functions that are called. That means the spool speed is synchronized, the puller speed is synchronized, the traverse is synchronized. And if there are any changes, like the user might have clicked something or changed the value in the meantime, then we check if there should be an update for the front end. And if there should be an update for the front end, then we basically send a new front end update with this function emit state. Exactly. And then we have the live values, which are the ones you can see in the graph, and they are sent at 60 frames per second. That means every 60th of a second, the function emit live values is executed, which then sends the live values to the front end. Exactly, that is the control loop of the Winder. The API of the Winder is a somewhat longer file, but here, for example, in the enum mutation, there are all the functions that the user can execute. That means he can set the function set traverse limit outer. That means setting the outer limit of the traverse, the inner limit of the traverse. And exactly, these are simply all the functions that the user can call, and they are sent via the REST API. Then there is, for example, the struct live values event, and here are all the values that are displayed in the front end, such as the puller speed, the spool speed, and so on. Then there is the other event, as mentioned, the state event, which only occurs when something has changed. And it includes, for example, what status the traverse is currently in, what status the puller is in, whether it is currently pulling or not, and so on. Or also the mode. Should the machine be on standby right now? Should it hold? Should it pull? Should it wind? Those are the three core things of the API. This is Yes, talked about having a checklist for each machine, which devices should be present, and that is basically the checklist for the Winder. That means, for example, it first checks for the bus coupler, then looks for an EL2200. And some terminals, they still need a certain configuration. That means if you have a stepper terminal for stepper motors, you can also set with which currents to operate the coils. That means, for example, there is a value down here, 6000 that we can set. That is then 6000 milliamperes for the coil of, that is then 6000 milliamperes for the stepper motor of the coil. Exactly, but there are many other files in this folder from Winder, and these are all the individual implementations for the algorithms of the load arm, of the coil, how it should accelerate, how fast it should rotate. This is all abstracted away in individual files. Yes, thank you, thank you. And since our software is open source, there are also people who look at our software, and we are proud because we already have 20 stars on GitHub. So stars on GitHub are just worth much more than Instagram likes. If you are also on GitHub, you can check out our repo and give us a star. And of course, some people are employees here, but there are also quite interesting other people who, for example, have looked at our repo. And we have now talked on the phone with someone who is simply from Malaysia and who has also worked with EtherCAT in Malaysia and has basically looked at our software, how we did it, and has now made like a university project out of it. And for him, it was also an inspiration. So it's quite interesting what kind of people also derive value from our open source project. Okay, here we can give a sneak peek into our secret development project. This is the bottle cap sorting machine. And here, for example, we train the model to track and recognize the caps. This is not yet the AI model we use for color recognition. This is a separate AI model, and it's YOLO 11. That means it's a really modern, cutting-edge AI model. And the cool thing is that we can integrate this AI model directly into our softwares. That means we have the AI model and the field bus and machine logic all seamlessly, all in Rust. That means we have no technology gap. We don't need another interface to connect between a Python and a Rust server, but we have everything seamlessly integrated, and we can use these cutting-edge models directly in our machine. And of course, assuming that we have the right hardware for it. And that's just really awesome, because I don't think you can implement such a model in such an old PLC, or at least not so easily.